to day 18 of calculus, sketching and interpreting derivatives. What we're going to do in this first function is, given two functions, given the graph of two functions, figure out which one is f of x and which one is f prime, meaning which one is the function and which one is its derivative, When you just have two functions, the best way to go about doing this is to check three things. Where is the derivative 0? Where is the function increasing? And where is it decreasing? And start by just picking one to be f of x and see if it works, because there's really only one answer or another. There's only two possibilities here. So let's pick the blue as the function. Let's check something here. So at these points, this point, and this point, the tangent line slopes are 0. The tangent line slopes are 0. The tangent line slope is 0 there too. So at each of those x values, if that blue function is the function itself, and the red function is the derivative better be 0 there. Well, it is 0 right there. It is 0 right there. But what about here? It's not 0 right there. So that tells us that the blue function can't be the function if the red function is going to be the derivative. So let's check it in the other direction. Let's check the red function. Where's the red function's derivative equal to 0? Well, it's right there, and it looks like right about there. At those points on the red function, the tangent line slope is 0. So let's check if it matches. Oh, look at this. Right there, the blue function is 0. Right there, the blue function is 0. And if you zoom in a little bit here, so it matches the zeros. So right now, it looks like the red function could be f of x and the blue function could be f prime. Where this function has a tangent line slope of 0 does match the blue function. Let's check increasing and decreasing. So where is the red function, the function we think of f of x? Where's that red function increasing? It's increasing here, and it's increasing here. So wherever the red function is increasing, the blue function better be greater than 0. Is that true? Well, look at this. The blue function does look like it's greater than 0 from here all the way to here, which is where the yellow is, and it's greater than 0 from here all the way to here. So it does match where the red function has a positive derivative. Where's the red function decreasing? Well, it's decreasing everywhere else. If the blue function is going to be the derivative, it must be below the x-axis. And look, it is. From here, sorry, I'll go to red here. From here and here, it is below. So what did we check? We checked where the derivative is 0. We've checked where the derivative is where the function is increasing or the function is decreasing. You check those three things. The easiest thing to check first are the zeros. Where is the derivative 0? So pick one of the functions, see where the derivative needs to be 0, and see if the other function crosses the x-axis at those points. And then also make sure you check where is the function increasing and decreasing to match. So now, given some conditions, let's graph a function that works with all of these conditions. So draw one function given all the following properties. So part A, it says f of 0 is 3. That means when x is 0, y is 3. And when x is 3, y is 5. So 3, 5, right there. So take the easies first. Graph the easy stuff. And what do we know? F prime, the derivative, is less than 0 and increasing for x less than 0. What does that mean? Well, f prime less than 0 means the function is falling, it's going down. But if f prime is increasing, it can be falling and increasing like that, it means that it's going to be concave up for x less than 0. So to the left of 0, so over here, everything that's going to be graphed in this area, the function has to be falling and concave up. So let's just draw something like that for now. So it's going to be falling and concave up to there. We can change it if we need to, but that matches part B here. F prime of x is greater than 0, which means that the function is increasing. So the function is increasing and for x from 0 to 3. So it's increasing. So I'll use green again from 0 to 3. So it doesn't say anything about concavity, but it's going to be going up from 0 to 3. So maybe we could just go like this. It's going up. And then it says that f prime of x is less than 0 and decreasing. So if f prime of x is decreasing, the function is falling. and decreasing means it's going to be concave down, concave down. So I'll use red for these things. So for x greater than 3, we know the function has to be falling and concave down. So it's kind of going to look like this. So it could be that, but let's smooth this out a little bit. Keep in mind for part C here, the part we did in green, part C, didn't say anything about concavity. So we could change this a little bit and make it so it goes, it kind of changes concavity there, make it a little smoother. Or if I zoom in a little bit, which you can always do, it's going to go up and then like that. So we have falling and concave up, rising, falling and concave down, and it's glued to those 2 points. So we have all of these conditions right here. Oops, I'll put that back there like that. Excellent. So now we're going to graph a function given the derivative. We're going to graph the function given the derivative. Again, start at the zeros. So we know the function's derivative is 0 in 3 places. That means that wherever the function crosses these x values right here, it's either going to be a highest point or a lowest point, a highest point or a lowest point. We've used yellow before for increasing, so where the derivative is positive, the function has to be going up. So that's going to be like this. The function will be increasing where it's yellow. The function will be increasing wherever that's yellow. And then below the x-axis means it's going to be decreasing. So let's start off with the zeros here. So we know that somewhere along this, the function is either going to have a highest point like this or a lowest point, meaning the derivative is 0. So let's just pick it. Let's say it's going to be a lowest point like this. It's going to be a lowest point. That's all we know. So if we started there, the blue here means that the derivative has to be negative, meaning the function has to be falling. So let's just make it falling. It doesn't say anything about concavity, but it's falling. And then where it's yellow, it has to be increasing. So let's make it increasing. But then when it hits this red line, the derivative has to be 0, meaning it's going to be a highest or a lowest point, and it makes sense to make it a highest point. And then it's going to be falling where it's blue, so let's make it falling. And then when it hits this red here, it's going to have to go back to rising like this. Oh, I kind of made that a little bit too far over to the right. It's going to be rising again. Now keep in mind, these 3 points right here, the point here, here, and here, I could stretch them down or up or down and wouldn't change anything. But the key thing is, wherever the function is above the blue, it has to be falling because the derivative is negative here because this blue part right here is below the x-axis on the derivative, meaning the function has to be falling. So the function is falling here and it's falling right there. The yellow is where the derivative is positive, so that means the function has to be increasing. So the function is increasing here and there, wherever it's correlating with the yellow part. So do the zeros and then do where it's increasing and decreasing. And keep in mind, these 3 points right here, 1, 2, and 3, they could be stretched up or down. That doesn't change. You don't know where it is, but you just know that it's where it's going, where it's decreasing and increasing, and where the derivative is 0 at these 3 points. So a dynamite blast propels a rock straight up into the air. Its height as a function of time. Height as a function of time is given by s of t, where s is measured in feet and t is measured in seconds. So what does s of 3 mean? Well, let's evaluate s of 3. That's going to be plugging 3 into here. 160 times 3 minus 16 times 3 squared. And you get 336 feet. And what does that mean? It means that at 3 seconds after the blast, the rock is 336 feet in the air. What about s prime? Well, it's the derivative, and remember, we don't need to use limit definition for polynomials. So s prime of t, it's just going to be 160 minus 2 times 16 times t. Remember, we reduce the power by 1 and drop the coefficient, drop the power to the front. So let's clean that up a little bit. So s prime of t is going to be 160 minus 32t. And it says s prime of 3. So s prime of 3, we plug in 3 into here. We end up with 64 feet per second. What does that mean? That after 3 seconds, or 3 seconds after the blast, the rock is traveling at a rate of 64 feet per second up. It's important to say it's going up. So to emphasize something that's important, units are important. So let's say we had the cost in a function where the cost C in dollars of building L meters of highways computed by some function C equals F of L. C equals F of L. So cost is some function of L. So what are the units of F of L? That means when you plug in L, you get into the function F, you get out C. C is in dollars. What are the units of L? L is in meters. So what are the units of f prime of L? The rate of change. Well, it's going to be delta the output over delta the input, which you've generally seen as delta y over delta x. But in this case, our output is dollars and our input is meters. So we're going to have dollars per meter right there. So what is the practical meaning of f prime of 100 equals 5,000? Well, we know that the input right there is meters and the output is dollars, like that. Remember how we plugged in 3 before and it was like after 3 seconds? So this is after 100 meters of road have been paved. It will cost $5,000 for an additional meter. So after 100 meters of road have been paved, it will cost $5,000 for an additional. Basically what this is saying is that after you've done 100 meters of road, you can buy additional, at that instant you can buy an additional meter of road at a rate of $5,000 for an additional meter.